Okay. Hi, everyone. I'm Yun Wang from Caltech. So now we're going to start this very exciting session. Please be seated and be quiet. I'm going to turn the sound so now everyone can hear you. Okay. All right. So our first speaker is Kalina Nedkova, and she's going to tell us from Johns Hopkins. It's Princeton. She'll tell us about unveiling galaxy evolution with Romans WFI. Yay!
Yeah, great. Well, thanks everyone for coming back from the break. It's great to be here. My name is Kalina Nedkova. I am a postdoc at Johns Hopkins University, and I work with Mark Rafalski here at Space Telescope. And I'll start this talk with a little bit of personal news, which is that I will be moving to Caltech IPAC for my second postdoc, where I will work as part of the Roman Galaxy Redshift Survey Project Infrastructure team with Yun Wang, who is the chair of this session. So it's a great pleasure to be here and have this opportunity to talk to you about slitless spectroscopy. And that is because these data allow us to gather spectroscopic redshift measurements of large galaxy samples, and they also enable a variety of other science, which I will touch on today. And then I will end my talk with telling you about how Roman will transform a lot of these science areas. And so here in my title slide, you just saw the direct images, followed by the GRISM images, where the light from every single object in this field of view is dispersed along a certain direction. And so the survey that I'll be describing to you today is called PASSAGE. It is a Cycle 1 JWST program with NIRISS, and it is also a peer parallel program. So what that means is that we took our observations at the same time as other primary programs that were not using NIRISS. And earlier today, Julie already mentioned that we can do something similar with Roman. For example, if we're observing with the coronagraph, we can also observe in parallel with WFI. And so in total, PASSAGE observed 63 independent fields. You can see the distribution of them up here. And if we zoom in on the Cosmos field, you see that we have about a dozen fields where we have the wonderful GRISM spectroscopy from PASSAGE, as well as the wealth of photometric data from a variety of facilities, including HST, JWST, and a lot of ground-based observations. And so these are fantastic because they have both very deep photometry and spectroscopy. And so just to give you a bit of a summary, we have 13 fields with 3 GRISM filter coverage from PASSAGE. And 5 of those fields also have RNC GRISM orientation data. And so this is very important because you can imagine 2 objects side by side. If you disperse the light in this direction, your spectra are going to be contaminated by the other object. Now, if you rotate the dispersion at which you're, in which you're dispersing the light, and at 90 degrees, you see that you can get very clean spectra for 2 side-by-side objects. And so with Roman, this will mean doing multiple position angles. You can see the breakdown of the other fields here, and I will just highlight that most of our fields are 1 GRISM filter, or have 1 GRISM filter coverage. And this is because we were restricted by the primary program, and so we could only change filter setup when the primary program was doing the same. So why am I up here telling you about PASSAGE? Well, it's because you can think of PASSAGE as a pathfinder for Roman. So here I'm showing you our 3 NIRISS GRISM filters, and here is Roman's. From 1 to 1.93 microns, you can see that these are very similar in wavelength range. And the data that we're getting with PASSAGE are stunning. So here is a redshift, roughly 2 galaxy. The spectrum here is shown in black. This is the F115 filter. This is the F150, and this is the F200. The gray shaded regions here are just the gaps in the wavelength ranges between our filters. Right, so the spectrum are in black. We fit this using a custom model. You can see this in red. and you see beautiful booming emission lines for this object. One thing to note is that the resolution of NIRISS is about 150. With Roman, we will do better. And so this will enable you to resolve lines that appear blended here. So for example, the O3 line, you see that it has this kind of strange bumpy profile. But with Roman, we will be able to resolve the O3 doublet. So this is very exciting and will enable a lot of new science. But despite its lower resolution, PASSAGE is still enabling a lot of exciting science. So I'll touch on 3 things today, but this is by no means a complete list. So we are studying the chemical composition of galaxies to constrain the baryon cycle. I will talk about this for the remainder of my talk, so I'll come back to it in just a minute. We are detecting brown dwarfs. So here in this plot, I'm showing you the number of brown dwarfs that we expect to find in the thin disk, the thick disk, and the halo of the Milky Way. These are really important because they retain the chemical composition with which they are born. And so they're fantastic for tracing the chemical enrichment of the Milky Way. And so these number distributions are for one individual field. And so you can imagine with 63, we're doing a great job. And then if you're interested in high redshift science, we're doing that as well. So here I'm showing you a Lyman alpha emitter. You can see the direct imaging here. It's a small compact galaxy, but it has a very nice Lyman alpha line. So you can see this here in the F115. It has both orientations, and then just a single orientation grism in the F150 and the F200. So if you're interested in this, please check out Runholm et al. 2025. We just published this paper, so please give it a read if you are interested in Lyman alpha. So let me focus on the baryon cycle. So the baryon cycle describes the interplay between all of these processes that you see here. The general picture is that you have a metal poor gas that's being accreted from the intergalactic medium. That's shown here in blue. This triggers star formation within the galaxy, which you see here in the central 30 kiloparsecs or so. This star formation produces stars, which themselves synthesize heavy elements and enrich the interstellar medium. And then this enriched gas is expelled through outflows driven by, for example, AGN or supernova feedback. And so these processes are not necessarily sequential, but they are all linked, and the baryon cycle describes them. One thing that's important to note is that they depend on the mass of the galaxy. So you can imagine a galaxy that is very massive, that has a very deep potential well, is going to be much more efficient at accreting gas from the intergalactic medium. And so what this means is that if we look at the metallicity of galaxies versus their stellar masses, we might expect to see a trend. And indeed we do. So this is known as the mass metallicity relation. We have the metallicity on the y-axis, galaxy stellar mass on the x-axis. And we see that low mass galaxies tend to have lower metallicities than high mass galaxies. This is because they are, compared to high mass galaxies, they have less efficient inflows of gas, which means that they have lower star formation rates, and then their outflows are also more efficient. On the high mass end, we see that these galaxies have higher metallicities. That's because they're accreting a lot of pristine gas, forming a lot of stars that are enriching their ISM. One thing to note also is that this relation is modulated by the star formation rate. So you see that galaxies with higher star formation rates lie lower on this relation than galaxies with low star formation rates. One thing that we're currently investigating, and I'm very excited about, is whether there is a link between this relation and the morphology of galaxies. So for example, we would expect that the baryon cycle also affects the way that galaxies appear. And so do galaxies that have really nice clumps, do these lie on a different part of this relation? So the way that we are measuring metallicity with JWST, so metallicity is just the abundance of oxygen relative to hydrogen. You'll see that expressed as 12 plus log O over H. And we need 3 emission lines to measure this. Those are the strong lines. We need O2, O3, and H beta. With the nearest data, we are able to detect those in two distinct redshift ranges, highlighted here in yellow. And at intermediate redshifts, we have recently shown that the calibrations that we need to derive metallicity from these lines works well. So this is really a great place to be looking at galaxy metallicity. So all of this is very important because if we look at the literature and we look at non-JWST results up here in the high mass end, and we compare these to recent JWST results, shown here in pink and black, what you see is two things. First, you see a shift in the relation on the y-axis. This is mostly driven by different redshift ranges that are explored in these works. But you also see a change in the slope. And this change in the slope tells you that there might be different baryon physics going on at the high mass end versus the low mass end. So is the baryon cycle different in these two mass regimes? Well, so passage is a fantastic way to answer this. So here are our individual galaxies where we measured the metallicity and their stellar masses. And you can see that, well, there's some scatter here. So if we want to understand these as a population, we can stack them. So we did. So we stacked them into 4 different mass bins. You can see some interesting trends emerge. For example, you can see that the O2 line is much stronger for higher mass galaxies than low mass galaxies. This is expected. But now let's look at that mass metallicity relation. So you can see, so these points here are our new measurement. And you can see that there is no change in the slope from the high mass end to the low mass end, according to passage, which would imply that there is no change in the baryon cycle between, or at least at these redshifts that we're exploring. So I think I'm running low on time. Yes. So I just want to say that I'm very excited about doing this with Roman. And so if we play a fun game of estimating the number of emission line galaxies we expect to detect, Roman will detect about 500,000 galaxies with O2 emission lines. And this is the weakest emission line that we need to measure metallicities. Oh, yes, and please check out Farhan Hassan's poster, who's doing this with lustrous TNG. And I just want to just give you a sense of the scale. So here is the high latitude wide area survey. This is the number of galaxies we will detect, where we can measure metallicity. For these, we can also do morphologies. And then here is the entire passage survey. So it's completely dwarfed by Roman. And so I'll just end by saying that Roman will reveal the details of the baryon cycle. Thanks so much for listening.
All right, so let's take a few questions.
Okay. Hello, I'm Chitapon Leverson from IT, and I have some questions. So you talk about the passage survey, and you talk about you are going to study the mass metallicity relation at high redshift. So I just want to know the redshift range and the depth of your survey.
Yeah, that's a great question. So we reach typical depths of about 26 to 27 mag. And the redshift range over which we can measure metallicities was in this slide. So because of the wavelength range of the filters, there's basically, if you trace these lines, you see that you can measure O2 and O3 in 2 different redshift ranges. And so these 2 redshift ranges from about 1.7 to 3.4 is where we can measure metallicity.
Any other questions? Okay, make sure I'm not missing anyone. Okay, all right, let's thank you for coming in.
Oh, yes.
Oh, okay. You can bring up the next. Sorry.
No problem.
Here.
All right. Did I get the title right? Yeah.
All screens, all screen.
Anything else?
What do we do to make it all screen?
View.
Oh, just run it, right?
Oh,
Maybe? Yes. Okay.
Okay.
So
Okay. All right.
let me know when I can go.
Yeah.
Okay.
So Sangeeta Malhotra, that we all know from Goddard.
Okay, thank you. So I'm Sangeeta Malhotra from Goddard, and we've been on this like a stubborn horse saying that while Roman is being designed to do a lot of great things, from exoplanets to cosmology, it can also do great stuff in the reionization era, which is about 12 point something billion BC, I believe. So I'll try to give some motivation and the feasibility of this sort of thing. And I think the previous speaker led into that very well. So what do we want to know about reionization? We want to know when, how fast, how slow. Mostly we want to know who done it, right? Is it big galaxies, oligarchs? Is it small galaxies, what are they called, plebeians? Is it AGNs, the weirdos? No, sorry, I apologize. So ultimately, who contributes, when does it happen? And we might even want to talk about how often did reionization happen, right? So if it's good enough to do once, you could do it twice, can we? I don't know. Let's move on. Everybody's seen this plot. This is reionization. That's when your galaxies and stars produced enough ionizing photons to ionize the gas around them and kill the chances of really small dwarf galaxies into forming, right? So maybe that indicates it's oligarch, but who knows? I'm going to keep an open mind, right? So there have been multi-wavelength reionization studies that have gone on. 21 centimeters redshifted, all sky surveys, EDGES, SARAS, they go into, hey, 17, redshift 17, hello, this is cosmic dawn. The method I'm going to talk about is Lyman alpha emitters. We think we are going to be right in the middle of the phase, but who knows? The SKA and MWA are also high redshift 21 centimeter things, and they are coming up to speed, and we'd like to have some synergy with them. And then Lyman alpha forest lines, they measure the sort of temperature of the IGM and say, hey, it was late. So maybe we'll find out the truth. So for the last some years, we've been doing ground-based narrowband imaging on wide fields. We find Lyman alpha emitters at redshift 6.9. So when JWST found them, we were not surprised, didn't lose sleep. And we find them clustered. So I'll just quickly go over that. Another narrowband thing at 7.7. 3 galaxies, Lyman alpha, due to their own emission, they're enough to produce an ionized bubble big enough that you could see those, okay? So once these little galaxies keep going, start going, 3 of them are enough. So I'm not just rooting for the little guy, but just small groups of little guys. But that's my personal bias. Anyway, moving on. So, and when you compare the sort of luminosity functions, the sort of distribution of galaxies, they're not vastly different from at redshift 7 from 6.5 or 6, which is already ionized, we think. So this is from Isaac Wolf's paper. The red line is our upper limit, and most of the uncertainty is due to systematics of converting the numbers to volumes, and I won't go into that. So at this point, many of you are like, JWST was built to do this with JWST, go away. So, and I'll tell you why JWST has delivered beautiful, brilliant, nice news for us. Very strong Lyman alpha at redshift 7.3, high equivalent width, so Lyman alpha is strong. And if the universe were neutral at redshift 7.3, Lyman alpha wouldn't be that strong. 10.6, I was like, I wasn't even shocked at that point. 13, I think the universe is showing off at this point. And then in addition to that, people are finding a lot more massive galaxies, which are massive and old, and like redshifts of 10-ish or something. I mean, they're better experts at that in this audience, so I won't go more into it. So, and a possible overabundance of ionizing photons. So you could reionize twice. Well, a girl can dream, can't her? A lot more low luminosity quasars and black holes, the little red dots. So in numbers, they make up for things, and they can be a significant source of reionization if you're keeping an open mind. So what does JWST not do so well? Statistics. JWST finds many strong Lyman alphas up to redshift 13, but these are 3 plots of ionization fraction derived from the Lyman alphas with JWST data. And here are the authors. And you'll see the error bars are large. So we need statistics to bring those error bars down, but we also need to offset the sort of systematic effect that one JWST field is about the size of one bubble or something. So we expect reionization to be inhomogeneous. So on the left, you see, I'm very proud of this. This is this plot we made long ago when it was all black and white, and then we colorized it. So this is the longevity of the problem. It hasn't gone away, and we still have to make Roman today. On the left is the ionization state in a simulation. White is ionized, black is neutral, and on the right you see where Lyman alpha galaxies are visible and where they're not. Oh my God, I've been going on and on. So let's put it in high gear. And a better plot is this. Right now, we have 3 major models: early reionization, late reionization, and slow reionization. So this is basically how the neutral fraction works as a function of redshift. And if you correspond those to simulations, you see how much sort of inhomogeneity there is, bubbles forming, going away, etc. And also shows the field of view of JWST and Roman. So Roman is the thing to do it. You could do better follow-ups after. So we've been trying to do the feasibility of this and quantification. We start with Roman light cones produced by Aaron Young. This paper is published, make ionized bubble calculations, Austin Gabriel Pillai, and then populate by Lyman alpha galaxies and calculate transmission in different directions. And this is what happens. The luminosity goes, the dark ones are with IgM in, where the neutral volume is about 75%, and the light ones are without taking the IgM into account. So you see there's some suppression of the number and luminosities of those things. And the similar thing on the right at a different redshift where neutral volume is 86%. So Lyman alpha takeaway message: Lyman alphas don't disappear. There's change, but not complete obliviation. So what do we hope to achieve with Roman? The blacks are what I've already been talking about, the points in black color. And the blue ones are aspirational. I'm hoping we'll be able to do that, cover enough area to enable cross-correlation with 21-centimeter experiments. Shout out to white paper for the decadal, Hutter et al. And then let me go to, can we do it? As they say in Bob the Builder, yes, we can. So these are plots of luminosity and flux. Flux left, luminosity. These are from Isaac Ball's paper. If you want more details, talk to him, not me. So we can do recovery of faint lines as faint as 1 × 17 at the 50% level. So both the signal to noise and the crowding allow it. So the crowding was the big thing that we wanted to see. And then calculations for prism. Prism is more sensitive. And these are from redshift 5.5 going to redshift 8. Same flux, 1×10⁻17, 20 hours instead of 40 or 80 hours. The pros are it's more sensitive. It can go to lower redshifts. Although JWST wouldn't tell you go to lower redshifts. But anyway, cons, it's lower resolution. So we lose some clustering signal, right? So GRISM resolution is very well matched to the size, the minimum size of a bubble that would let you escape Lyman alpha. Do I have more stuff? So this is a story that's, I think we're mostly there in the answer. It's to be continued. This is based on work done by SPQR team. They put me up there because I do bad jokes. That's my role. James Rhodes is the PI. Isaac Wald is here. Tree might be here. Aaron Young is here. Talk to them. I should also advertise that there's a spectroscopy data challenge is on. It's meant to be beginner friendly. Sign up. And here's the QR of the SPQR. Thank you.
You finished early.
I finished early. Man, I was lied to. No, I
20 seconds.
I have 20 seconds. Never mind.
Okay, you get an extra point. All right.
20 seconds. Let me thank all the people who, engineers, everybody, budget people who have made Roman possible. Roman was not built in a day.
Yeah. Perfectly used time. Okay, questions?
That was a really fun talk. I really loved it. At one point you mentioned that potentially you think reionization could have been 2 events. So are you saying that like that we could resolve it into 2 distinct periods of reionization is what you're thinking, or am I?
So there are papers saying we have too many ionizing photons by the time, you know. So suppose you did reionization at redshift less than 10, greater than 10, you'd be able to ionize. You'd be able to recombine again and then do another ionization. It's not a new idea. Renu Chen wrote a paper about it in mid-2000s. Yeah, look at me say mid-2000s, like the young kids. So, yeah.
Thank you.
Other questions? Okay, raise your hand high so I actually can see your hand. Yes, in back.
Can you say more about the spectroscopy data challenge? What is the goal?
Okay, so the goal is more pedagogical than anything else. So, but we want to cater to all levels of folks, beginners to advanced. So, we were going to do a session, in-person session in Alaska meeting, but we weren't able to. So the second one will be hybrid. Please sign up. And the thing is, ultimately, so we'll build up expertise, we hope, and then ultimately give people a piece of the sky, right? And say, find all the emission line galaxies or find brown dwarfs or something like that. So as part of that, we've taken Cosmos Web data and made simulations based on the actual structure and clustering of galaxies, and to have crowding. I think Isaac is going to talk about that in his poster presentation. Find Isaac, he's the man.
Okay, we can take a final question. Anyone? I'm looking. All right, let's thank you.
If you want something.
You can give it to me. Thank you. Okay.
Okay, thank you.
So, okay, great. Okay, so we need to get out of this.
Got it?
How do we?
That's good. That's right. Yeah. Perfect. Okay. Okay.
All right, next we'll have Yongmin Liang from NAOJ to tell us about some more exciting stuff.
Okay, thank you very much for the introduction. I'm Yongmin Liang. Now I'm a postdoc at NAO Japan. And today I would like to introduce a very interesting large-scale structure at cosmic noon. There are a lot of cosmic in my title, but they are representing the how and where cosmic extremes, and also what the cosmic Himalayas, a new structure we named it from last year at the cosmic noon. And first of all, let me go to the introduction. This is a very famous picture from Hopkins 2008. And once a galaxy undergoing the mergers, they can produce the inflow gas to trigger the starburst and also the supermassive black hole growth. And also there can be the dust. And such kind of feedback from the black hole can expel the gas and making the central region to be clear. And also due to the supermassive black hole growth, they can be more luminous, which is known as the quasars. This is from the theory, and from the observational side, actually we indeed have some previous support from ground-based telescope like the Super Rho Hyper Supreme Cam. They utilize the such kind of survey data to identify the mergers and non-mergers, and they do find that there can be the higher AGN fraction for the mergers compared to the non-mergers, up to the redshift 1. And recently, of course, Euclid can extend such kind of study to the relative high redshift, like to 1.5 up to 2. But to the more, to the higher redshift, and especially for the quasars, which are very luminous, and the host galaxy morphology are difficult to identify, we need some indirect indicator, like the environment. And actually, we do have some kind of suggestion, like from the surrounding of the radial route AGN, we do find the number the galaxy number density can be higher compared to the average field. And also, if we focus on the quasars and the pair, you will find that they seem to be more associated with the surrounding galaxies and tracing the protoclusters. So a natural question is, how about the more extreme cases, like quasar clusters? And that's what we try to find in the past. This is the heat map of the quasar density in the sky, exactly from the Sloan survey. And this, you can easily identify a very clear hot peak in the Z0 to 10 field. If you check the distribution, you will find that actually this field is so extreme that in the comparable region, normally you can find none or even just up to 1 quasars. But in this field, you can find 11, which means 17 sigma outlying regime. This is for the quasar, so we are interested in their environment. We try to perform the narrowband imaging utilizing the Super Rho Hyper Supreme Cam. So the narrowband can map the line alpha emission at a specific redshift utilizing the narrowband exact technique. And this is the result. The points are the line alpha meters, and the blue color indicate the contour of the density. And the orange crosses are the quasar location. We once expect to find massive halos around the quasars chased by these galaxies, but we do find some high density clumps of the galaxies, but they show somewhat 25 megaparsec offset to the density peak of the quasars. If you just check their density distribution, it will look like this one. Furtherly, we are also interested in the gas properties, like we try to check whether there can be the agent candidates by looking into the NUV band counterpart. You will find that most of them are shown as these black crosses are more clustered around this clump A, while they avoid the central part of the clump B. And we try to search for the extended line alpha emission, which means the extended CGM emission. labeled by the square, they are more around this clump B while avoiding the clump A. Seems to be this clump can be more, gas rich. So then we are interested in the underlying gas distribution. But at the ratio 2, IgM is so diffuse and cold, so it's difficult to directly map their intensity. Instead, we try to utilize the Lyman-Four forest. Just as an example, this is this star is one line of sight, so you can predict the intrinsic continuum by utilizing the PCA fitting, and then by contrasting the observed flux and the intrinsic continuum, you can derive the transmission. And further compared to the cosmic mean, you can derive the fluctuation. This is for one single line of sight, and when you have multiple line of sight, of course, you can do the smoothing to reconstruct a three-dimensional distribution. But because this is the long quasar, so actually the spatial distribution is relatively coarse. So the smoothing scale is around 10 to 20 megaparsec. And this is the result. The blue color indicates the more transparent and more ionized region, while the red color indicates more neutral or more opaque region. An interesting thing you can directly find by eye that the two clumps of the galaxies seem to chase totally different gas in the ionizing gas status, and the clump B do chase a more gas-rich region. While interestingly, again, the quasars themselves are located in the boundary, and the profile shown in the right-hand side is just to quantify this such kind of things from the visual check. Two clumps of the galactic overdensity, while the transmission curve can have a very significant transition. And actually, that's also why we call it as the cosmic Himalayas, not only because of the density peak of the quasars, but also such kind of peak are separating totally different cosmic structures, just like the geological structure on Earth. So if you are interested in this structure, you can directly search for this name. So one interesting thing we would like to think is whether the quasars can contribute to the ionization of the IgM or not. So a straightforward way is to look into their luminosity and their local environment indicated by the IgM. You can easily find that the more luminous quasars do be located at the more transparent region, and that shows a very good correlation. But again, I should mention that actually this IgM is measured on the 10 to 20 megaparsec scale, a very large intergalactic scale. So, but still we can find such kind of relation. And if you look into the individual slices, these are the different redshift frames. It just look like you can fly through our line of sight direction. And the circles are indicated by the radius. That means within the radius, the quasar ionization supports the ionization from the UV background. So you can easily find that from the different redshift size. It seems the joint contribution from the quasars have a very important contribution. And so now we have an important question: why there are so many quasars are triggered? Why no many galaxies are around? We are considering two possibilities. One is that maybe these are two individual substructures, and they are just undergoing the merging phase, just like the Bully cluster in the local universe. And if you consider the evolution of the size of protocluster, they can evolve to such kind of system. And on the other hand, maybe they are chasing the different cosmic filament, like the quasars are chasing more massive galaxies, and the LE are chasing the low mass galaxies. So in either case, it seems the massive galaxies are more important. And we have the J70 follow-up, and the black circles are the SMG selected from the J70 Scuba 2. And interestingly, you can find that these quasars are also showing a filamentary structure, not only on the vertical direction, but also on our line of sight direction. And if you compare them with the Lyman meter, you can find also, again, the offset. Looking into the most luminous SMG candidates, you can find that most of them are quite red objects, and also in many cases they have some multiple components. If you just go back to the Hopkins picture, they may be the merging system undergoing the dusty phase, and they can be the pre-quasar phase objects. And what we are witnessing from the quasars are the ongoing quasars. And if you just go back to consider here, they are mostly ionized. Why we do not find the powering sources? So they can be the faded quasars. That means the spatial distribution is very important, and you can even find the gas evolution within a single structure. Now let's go back to the space-based observation, the latest grism. Because we are now just focusing on the star-forming galaxies, but how about the other galaxy population, like the passive galaxies? With the latest observation, actually we can identify like the Balmer absorption and also the Four-Southern break. And also, why for the star-forming galaxies, we can also try to inspect their properties, not only just single emission line or continuum. And actually, Hubble Space Telescope is very powerful on such kind of at the redshift 2, and Loman do surpass its power. And once we have such kind of observable, like the DN 4000 and the Balmer absorption, you can indicate the galaxy ages, and also like from the O2, O3 emission, you can have the indicator of the O2, index to indicate the metallicity. There can be the offset compared to the cluster region and the field, just like the previous study showed. But now we can apply such kind of study into a single structure to see the spatial distribution. And they may throw up some trend. That's totally new, not totally new beyond the statistical analysis. However, the difficulty is that the field of view, this is a structure extending for 1 degree, means it is a 100 megaparsec scale structure. So if you utilize the Hubble, if you need hundreds of the pointings, that's totally invisible. But now if you have the Loman, just 2 or 3 pointing, you can fully cover the single such kind of structure. And of course, this is just one of our cases of the protocluster at high redshift. And in the future, if we can construct a larger sample, you can do such kind of things for the spatial distribution. And so that's all for my talk. I introduced cosmic Himalayas as an example to demonstrate how Loman mattering for the high redshift large scale structure study. Thank you very much.
You can raise your hand high. Yeah.
So you mentioned black cluster as like somewhat similar to the scenario. Do you see a lot of craters in black clusters?
Sorry. You mean this one, right?
Yeah. Potential reason why there can be many craters, like you are saying, one analogy situation to black clusters that we have completion of them?
Yeah. How to say, one of the possibilities we are now considering is that undergoing the protocluster merging, intergalactic gas may be easier to lose their momentum, to inspiring to the galaxies, and furtherly to inspiring to the center to trigger the quasars. And in the bullet cluster, actually we do have such kind of suggestion that in between they have the higher AGN fraction. Thank you.
One more question, anyone? Do not see any hands. Oh yeah, okay, 2 more hands.
Yeah, I guess our next step is for those quasars that trace the black cluster are then visible from high resolution SAMI data, where you get the CID curves from because those and could this be also over this region in those data where we can then use to select a larger sample?
You mean from what kind of survey?
For example, other kind of cosmology telescope, there is SAMI data, and you can select CID emitters from those.
I haven't checked those data. We once try to inspect the radio data, the whole sky surveys data to see whether we can find a comparable structure, but that's not the case. And also, actually, just from our field, we do not find many radio counterpart. Yeah, from the relatively shallow old sky survey.
All right, you get to ask your question. It would be good if you make it quick.
Yeah, no, very cool result. I'm curious to test your interpretation of maybe hot gas. Do you have any X-ray data, or are you planning to propose for it?
Yes, actually, indeed, we are proposing.
Okay.
Yeah.
Cool.
Thank you.
All right, let's thank our speaker again. Turn it off, and you put it down and we turn it on. All right, our next speaker is Dutrapon from CHESS. Okay, sorry, that's, oh, you're from here.
I'm from Rochester. No, from
Space Telescope.
Rochester Institute of Technology.
Oh, okay,
From
Rochester. Oh, yeah, I know your advisor. Okay, yeah. Or you should put your
Yeah,
institution on there next time.
Yeah.
Okay. All right. Welcome. Please tell us, should we applaud now or later?
Let's do it now.
Yeah, yes.
Okay. All right. I'm Chitrapon Lepasatpong, and I'm from Rochester Institute of Technology. I'm a fourth-year PhD student working with Dr. Jehan Patasese, and today I'm going to talk about how to improve density map of galaxies using the Candel's Herschel Environmental Spectroscopic Survey or the CHESS survey. So let's get started. Whoops. So let's look at some beautiful pictures first. So we have like pictures of a lot of galaxies right here. And one thing that I'm sure that a lot of people know that in dense environment usually suppress star formation of galaxies. So in the less dense environment, we usually see a lot of star forming galaxies. And in very dense region, we usually see a lot of quiescent galaxies. So that's what we know. And especially in local universe, we know that we know what we call SFR density relation. So in dense regions, SFR usually go down. But when you look at redshift greater than 1, we start to see some conflict in SFR density relation. So some research paper, they argue that there might be some reversal in SFR density relation. So when density goes up and SFR doesn't go down, it's like just reverse the relation. But some other research papers still argue that there's like no reversal or there's like flattening of SFR density relation. So we have some kind of conflict right here, and that's the goal of my research, is to study why does this happen and how we can improve the SFR density relation. We can just, so what's the cause of this discrepancy in SFR density relation? There are two possible causes here. So the first one is the insufficiency of spectroscopy at high mass galaxies. So we know that at redshift greater than 1, we usually rely on photometric redshift because that's pretty easy to obtain. Meanwhile, getting spectroscopy is very tedious and time consuming, and sometimes it's just a lot of faint galaxies, extremely difficult to get spectroscopy. So we usually rely on photometric redshift. The problem is that photometric redshift is not that accurate. The precision or accuracy of photometric redshift is not that high. And we also have, second problem is that when we look at higher redshift, when we look at star forming galaxies, when we perform SED fitting, we use data from UV to IR, and sometimes at redshift higher, we might need far IR measurement because we measure a lot of dusty system, and those dusty system we need far IR as well. All right. Okay, so for the photometric redshift, we can see that if we plot a plot between photometric and spectroscopic redshift, we know that there might be some uncertainty, and at redshift around 1, the uncertainty can translate into the distance of around 100 co-moving megaparsec, which is like huge, and that just not enough to obtain density maps. So the first problem that we need to
fix is that we need to get more spectroscopy if we want to map the environment accurately. So that's why I introduced you the Candle's Herschel Environmental Spectroscopic Survey, or the CHESS survey right here. So in this survey, I used the Keck DMOS instrument to obtain additional spectroscopic redshift of galaxies in 5 Candle's fields. So we have Cosmos, UDS, EGS, good north and good south. And for the CHESS survey, we just use only Cosmos, EGS, and UDS because for good north and good south, we already have a lot of spectroscopy. So we want to focus on the fields that have less spectroscopy. We have a large area of 0.2 square degree, and we focus on massive galaxy with stellar mass greater than 10 to the 10 solar mass. So that's the focus of this research. And that also relates to Raman telescope as well, because Raman telescope can do the same thing with larger area. So this is more like a prototype of research that we can do with Raman as well. But Raman will have much larger field of view, and that will help the research even more. But this is like an introduction to see what Raman can do as well. So I just want to introduce the result of my research. So we have 740 new spectroscopic redshift from the CHESS survey at the redshift range of 0.5 to 1.7. And we also obtained some serendipitous objects and some high redshift Lyman alpha Fuller objects as well. So apart from spectroscopic redshift, we also obtained some additional emission line fitting. So we fit some of the O2 line and H beta and O3 line as well. So we obtained around 312 emission lines from galaxies. So that's like the data that we obtained. So a lot of data is pretty noisy. So we were able to get around 300 galaxies that we can obtain emission lines. Apart from the CHESS survey, after that we create a CHESS catalog, and we combine the data with archival spectroscopic catalog to create the overdensity maps of galaxies to study how the number density of galaxy affects the star formation rate of galaxies. So that's the process of how we combine the data from the CHESS survey with other archival spectroscopic catalog. And we also use the photometric redshift from other galaxies and combine to get additional data like this. The next step of my research is to create a surface density measurement. In this way, we create a redshift slice and create the density map using the process called Voronoi Monte Carlo method. So in this process, we create a space segmentation method that in the high density region, we will have small cell, and low density region, we have large Voronoi cell. And in this method, we can quantify the surface density using 1 over the area of Voronoi cells. So that's the method that I use to measure the surface density of galaxies. So that's the density map that I obtained from the CHESS survey. So this is like one redshift slice that I obtained at this redshift range of 0.85 to 0.95 right here. And this is for 5 Candle's fields right here. And when I combine CHESS data into the density map, we can see that we obtain some additional overdensity regions. So that's the demonstration of how the CHESS data can improve the overdensity map of galaxies right here. So for example, this is Cosmos and UDS and EGS like this. Now, the next step that I'm working on right now is to do the SED fitting to obtain star formation rate and other properties of galaxies. So the most important part is right here, which is like I use the Herschel data to obtain far infrared data right here. So that this covers the dust emission of galaxy from dusty star forming systems, and we can see that this is like the important part that I add right here to improve the measurement of star formation rate. And hopefully from this process, we should be able to get SFR density relation. So this step is still in the work, and there's still like some problem. I think I need to readjust some parameters from scale because right now the fit doesn't fit well right now, but it's just like a work in progress, and I need to work on it a bit more. And one thing that I want to talk about is that since this is Roman symposium, I just want to make sure to talk about Roman a little bit more. So the advantage of this project is that this study is like a prototype study that we can apply to Roman, because environmental study of galaxies require large cosmic volume, and we require a lot of spectroscopy, as I mentioned in my research. So we can see that large cosmic volume, Roman has a really large field of view, so that will cover a lot of cosmic volume. We also have prism spectroscopy, so we can see that this type of research is something that we can do with Roman Space Telescope. So that's the overall idea of my research. So yeah, in this presentation, I have only 10 minutes to present everything, but there's still a lot that I want to talk. So please feel free to meet me after, like during the break, and I can talk more about my research as well. But yeah, this is my conclusion. So we present a lot more spectroscopy from CHESS catalog and some density map as well. So yeah, feel free to ask me any question. Thank you.
Okay, we have plenty of time for questions over there.
Yes.
Great presentation. I really like what you did. And I was curious, were you able to quantify or calculate how much the increase in SNR was when you add chess to your images? Because we saw there was an increase, but did you quantify it by chance?
To quantify the overdensity, right?
So you had like the overdensity with and without chess?
Yeah.
Do you see how much it increased by?
Yes, there's like some increase, but yeah, I can't remember the exact number, but yeah, I have my own data right there, but there's some increase.
There's a request for you to quantify the gain.
Yes.
Other
Right.
questions? Raise your hand high, okay? Don't be shy.
Yes.
Yes, from there.
Just curious about whether you have some plan or method to evaluate the cosmic variance for your upcoming Z versus star formation rate, because I think the current area is like quite too small to conclude anything clearly, right? So
Yeah, so to quantify the cosmic variance, right? So right now, for my research, I haven't reached that step yet, but this is something that I will need to consider in the future step of my research.
Okay, you had a question?
Yeah.
Very cool stuff. I agree that Roman's wide field capabilities will be very important for galaxy overdensity studies. But do you have a sense of how large a field of view, or what size area do you need to really look at other things as a function of overdensity? Do you have a number? Do you have a sense of that?
Yeah, that's a great question. So I know that for Roman, it will have much larger field of view to study the galaxy, and that's also one of the goal of the CHESS research as well. So for the CHESS research, we use all five fields of candles, because we know that we need, for environmental studies, we need a large area, and we want to have different fields to make sure that we don't have any bias when we study. So we use 5 fields, and right now this is we use the area of 0.2 square degrees, but for Roman, it's going to be much larger than that, and we can cover much larger area of the sky, and I'm sure that will also reduce the bias and make sure that we get the overall understanding of the environment in larger area too.
All right, let's thank our speaker again. We have one more talk. Yeah, here you go. Yeah, so you put it on and we turn it on. Oh, so after this, don't go away, group photo. Outside. Oh, okay, it's outside.
Assuming it's not raining,
Oh, okay.
which I don't think it is.
Follow the crowd. Don't be left out in a group photo.
Be able to go out.
Please.
Oh,
On the front steps. Okay, on the front steps. Should not be raining. I checked the weather this morning.
No, it's not raining. You probably know more than I.
Oh, how do we make our screen? Sorry.
Yes, I was trying to.
Your most incompetent chair. I only found out I'm chairing like just before the session. Somehow. Okay, so. Slide. Okay.
I always hate this stuff. Should be a slideshow. No.
What happened? So before just, oh, yay.
Yeah, it works. It
It
works.
looks like.
Okay.
Thank you.
But
Okay.
is it?
Yeah, we need to turn it on.
Uh-huh.
Now it's on. So our final speaker for this session is Ho-Jin Cho from Texas Tech University.
Yeah.
Will tell us about
Yeah.
cool stuff.
Yeah. I hope you are not too hungry right now. So I'm Ho-Jin Cho from Texas, postdoc from Texas Tech, and I'm gonna talk about the Asian reverberation mapping study using Roman highlighted to time domain survey, which I think this is the only talk related to this topic, which is surprising because this is the Roman Space Telescope is made for this kind of studies, and this is very important in regarding the galaxy evolutions and cosmology aspects. So the torus is a warm and optically thick molecular medium surrounding the AGN, which obscures the AGN energy output towards a certain direction. This is why we have something called type 2 AGNs, where the accretion disk is obscured from the observer via the dust torus. How much the dust torus covers is called covering factor, and this is important in understanding the black hole galaxy coevolution, since it can restrict the influence of where the AGN feedback can reach. But the shape of these dust torus is still not known very well. So assuming it is actually a torus, the curvature of this inner surface of this torus is can reflect the accretion physics, radiation pressure, and dust characteristics surrounding an AGN. Observational evidences of a few handful of AGNs also support that the tori are conic concave shaped. The question is, how much? To answer these questions, we can use something the AGN folks have been using for a long time, which is called reverberation mapping. This is measuring the cross-correlation between of the light curves between different bands to understand the various characteristics of the AGNs. In theory, we can infer the AGN torus structure by fitting the light curves in infrared. And this is where the Roman highlighted time domain survey comes into play. To test how useful this time domain survey would be, we ran a series of simulations as follows. We first generated hundreds of AGNs, and we realized their continuous light curves for each of the AGNs. And sampling these continuous light curves and randomizing their fluxes to match the characteristics we expect from the Roman highlighted time domain survey, gives the mock observational results. We fit the light curves from band 1, 2, and 5 from each tier and I will explain what that means later, and collect the results into statistics. And we developed a new code for carrying out these two steps, which we decided to call this new code MARY. This code computes the agent transfer function by integrating the mesh model of this agent torus surface or disk surface, and given a geometry and thermal profile. And it also computes the Gaussian process likelihoods given observed light curves. So here are the wireframes of the mesh disk structure and the time lags given the mesh structure and the responses at each of the cells. So this code is still under development, but we are planning to finish this by the end of this year and make it public. For the geometric structure for our assumed model, we just use this axisymmetric surface model, which is inspired by the slim disk model by Abramovich. And for the thermal profile, we just adopted piecewise power law function for theoretically modeled for the dust torus. This is an example for the simulated light curve. So on the left, we have a so-called transfer function of agent light for each band, which is just a convolution kernel for each kernel, each band from the driving light curves, which we think is from the X-ray or very high energy bands. And this convolving those light curves gives the light curves of the respective bands, which you can see on the right-hand side. So top panels are the driving light curves, and these black lines at the bottom panels are the continuous light curves, and the colored bars are the realized Raman fluxes. So we have, so by band 1, 2, and 5, we mean these and these. So we fit these light curves, and the time window are focused on the core survey of this time domain survey. And we fit this using the nested sampling, which is ideal for obtaining the parameter posterior and the model evidence. This way, we can see whether the thick disk, thick torus model or flat torus model would fit the individual light curves better, or how much better. And which we quantify this as sensitivity. And also, within the same model, we also determine how much we recover each of the model parameters. And we simply, if we determine a parameter of a model, is it recovered if it falls within 3 sigma or anything equivalent. So here are some of the results we have for the simulation. First, discerning between the thick torus and the flat torus, we have a sensitivity of a thick input model as a thick torus, which shown in black, above 60%, given all of the redshift, flux, and the luminosity ranges. And this is the case for any kind of inclination, covering factor, or curvature combinations. And you can see that for this, when the curvature is flat, which means if it is basically conical torus, it is a little bit difficult to discern the model from the flat torus, but it is still at 50%. And if we compare between the wide tier survey and deep tier survey, wide tier survey has a little bit reduced sensitivity due to its shallower depth, but it is still overall 70 to 80%. Deep tier is in particular useful for the low flux or low luminosity AGNs. And if we assume that we know the luminosity of individual AGNs or redshift of individual AGNs from different observations such as X-ray or LSST or spectroscopic surveys, then we can just give the priors for those parameters, and it increases the sensitivity by slight margins, and it is especially large for the highly flat and conical tori. For parameter recovery, it is overall very large, above 65%, and it is still larger for the deep tier surveys. And if we impose the priors, actually for the covering factor, it gives a slightly decreased recovery rate for the covering factor parameter. And it is because I think it makes the model a little bit less flexible, and it may require some additional information like agent variability information from the X-ray or UV light curves. And so to talk about how many agents we are talking about from the Roman highlighted time domain survey, we did the similar statistics computation in two-dimensional in redshifts and the luminosity, and also drew this agent luminosity function in similar manner, and we multiply these to obtain the cumulative number of agents observable at given redshifts. And these are the results. So for the sensitivity for the local agents, we have like about 50% sensitive for the local agents, but at the higher redshifts, the sensitivity increases to about 80%. At redshift 0.8, this increase is due to there's a more higher luminosity AGNs at the high redshifts. And in total, we expect to see about 500,000 AGNs in wide areas, a wide tier survey, and 250,000 AGNs in deep tier survey that we can discern the geometry. This number is unprecedented. We also see similar numbers in the parameter recovery, but I won't go into the deep details. So this is the largest sample of the agent reverberation mapping ever carried out, outnumbering all of the previous reverberation mapping sample combined, regardless of the bands, and by the orders of magnitude. So this will be extremely useful in all kinds of galactic evolution, agent physics studies. So I hope this talk convinced you into looking into this. And also, I have no time, so I should stop, but this might be also useful in the cosmology studies as a standard, but ask me later. So I will leave you with the summary slides, and thank you very much for listening.
Oh, so first I want to respond to what you said. So I think when you began your talk, I think the most exciting thing about Roman is that it's so capable, almost everyone feels like it's made for them. It's exactly what NASA wants, so great, power to everyone. Questions? I know it's so late, people are hungry, but if you have an urgent question, you can ask. Oh, yes.
So when you're doing AGN spectrometry, what would you want as sort of a reference epoch? Would you just sort of have an overall floating flux, or established flux that you just reference range, or would you have statistic models for the galaxy and then you're trying to point source on top of it? What would you actually want for the spectrometry?
So it's a little bit difficult to say because we don't have a good statistics about agent to host galaxy fractions as a function of redshifts. And I think this also needs to be a little bit more studied. But right now, I'm just assuming that all agents are point-like sources, which would be the case for the higher redshifts. But yeah, I think this needs a little bit more research.
All right, so let's wrap up. And if you have questions, just catch Ho-Jin at lunch or coffee break later. Let's thank him again. You want to announce the group photo again?
No, just lead the way.
I'm gonna open this.
Perfect.
Yeah, this is close.